Greetings, welcome to lecture number 13 on basic circuit theory. I am Razavi. Today we will look at another electric device, namely the capacitor, and understand its properties and the equations governing its behavior. So we're going to start with the definition of capacitance and see how it plays a role in the I-V relationships of capacitors. And then we will extend these ideas to electric properties that capacitors exhibit and why they become interesting in circuit design. But before we go there, let's take a look at last lecture. We talked about a bunch of ideas. We talked about source transformation, and we said that in some cases we prefer to transform a circuit like this, which is a Thevenin equivalent, to a circuit like this, which is a Norton equivalent, and vice versa. Because sometimes it simplifies the analysis if we go to here, because it's possible that this resistor can be merged with another resistor somewhere else. We talked about the concept of energy and power. We saw that energy and the voltage difference can be related by this equation. So if we take a small amount of charge across a voltage difference of V, then the energy necessary to do so is given by V times dQ. And from here, we see dE over dQ is to V. And now we can go ahead and find the power. The power is defined as the time derivative of energy, meaning how fast energy is consumed or delivered or drawn. And that came out to be V times I for any condition at any time. So this is a very useful quantity to remember. And then we extended this to resistors, and we saw that for resistors it can be simply written as V squared over R or I squared times R. Okay, and final concept was maximum power transfer. We said that if we have a circuit of this form, which can be modeled by a Thevenin equivalent, and this is driving some sort of load resistance, maybe as part of another circuit, and then the power delivered by this circuit to this load is maximized when RL is equal to RT, provided that what is variable in this optimization is RL, meaning RT is constant. We play with RL to maximize the power transfer, and that happens when RL is equal to RT. Okay, so now with all of these ideas, we can go ahead and look at capacitors. Capacitors add considerably to the library of devices that we have and make the circuits that we can build much more interesting. All right, so we're going to start with a simple experiment just to see how a capacitor comes into picture. So simple experiment. All right, I'm going to take a voltage source, so like a battery, having some voltage V1. So we buy a battery of 1.5 volts, and now we will connect it through a switch. So we have a switch here to two conductive plates. So two metal plates, for example, right? Just like this, parallel plates. So we have a plate here, we have a plate here. This goes here, and this goes here. All right? Okay. So now, at time 0, I go and turn on the switch. I close it. And I just look at the circuit to see what's going on. All right. Well, we know that this switch is ideal. These wires are ideal. So the voltage difference that we measure here, for example, 1.5 volts, is present everywhere between these two wires, right? So as I come along and I see and stand here, I still measure a voltage difference equal to V1. All right, so if I put my voltmeter right here and measure this voltage difference, that's still 1.5 volts or V1, so that's V1. Okay, now I look at these two plates closely and I observe that I have a voltage difference of V1 between here and here. That voltage difference can exist only if an electric field exists between here and here. This is something you remember from physics. Remember the relationship between the electric field and the voltage. So that requires that an electric field be generated from here to here, and the lines have to be oriented this way, from positive to negative, from high to low. All right? Okay. The next part of our thought process is, if I have an electric field, then I must have charge. So I must have some positive charge on this plate and some negative charge on this plate. Right? So that the electric field lines start from the positive charge and end on the negative charge. So what we see is that after we connected this structure to this battery, we ended up with some positive charge on the top plate and some negative charge on the bottom plate, and we have a voltage difference of V1. All right. Now let's go ahead and open the switch, turn it off. Then what happens? Okay, so I'll change the color of my pen, and I say let's open it up. Well, so now this is disconnected, the battery is out of the picture, and we have only this structure left. This structure has still charge on it, right? The charge is still sitting here and here. So that structure, if I just draw it by itself, has charge. So plus charge here, minus charge here. And if I connect this to something like a resistor, what happens? So let's connect it to a resistor. Well, the positive charge begins to flow through the resistor and comes back here and cancels negative charge. So a current begins to flow through this structure and through the resistor. And as the current flows through a resistor, as we saw last time, the resistor begins to burn power. So in other words, the resistor begins to waste energy. So that means that this structure has energy in it, and that energy is now given to the resistor, and the resistor is dissipating it in the form of heat. So this says that by the act of connecting this battery to the structure, I gave it charge and I gave it energy. And later on, I could try to use that energy to do something, right? So this little experiment tells us that if I take a structure like this consisting of two parallel plates, I can charge it and I can discharge it. And this is what you would call a capacitor. This capacitor receives charge or loses charge, receives energy or loses energy, right? Depending on how we configure it. All right, so one note I should make about this experiment is that we see that we have positive charge coming here from the battery onto this top plate, and then a negative charge coming from this side of the battery coming to this plate, right? This charge had to come from somewhere. It came from the battery. Now, that's one perspective, but another perspective, which is actually more correct, is to say that yes, we brought positive charge here, okay? And the charge must be conserved. So if I'm taking positive charge out of this battery this way, I have to bring positive charge back to the battery this way. So if I bring positive charge this way, I am taking positive charge from this plate of the structure. And if I take positive charge away, I leave behind negative charge, right? So it's really charge conservation that requires that whatever charge we have on this plate, we also should have the negative of that on the other plate. These always go hand in hand. It's not possible to have charge on one plate and no charge on the other plate. Okay, so this brings us to the definition of capacitance. So definition of capacitance. Now, taking a step back, you remember that for resistors, we said the resistance is just given by the voltage divided by the current, right? It's a simple experiment. If I give you a device and I say how much is the resistance, you can hook up a battery, apply voltage, measure the current, and divide to find the resistance. So the question is, if I give a structure like this, and I say how much is the capacitance, what do we do? How do we go about determining that? Okay, so it shouldn't be that hard. The idea is as follows. I have my symbol here, so that's the symbol for a capacitor, as you can see sort of from here. And let's call this capacitance C1. We don't know how much C1 is, and we want to find it. What we will do is we will bring some positive charge onto the top plate, so plus Q, and hence some negative charge on the bottom plate. All right, where does it come from? It can come from anywhere. It can be like this, it can however we want to do it. So initially the capacitor has no charge on it, and hence it has 0 volts on it. And now we brought this charge. When I place this charge on this plate, positive, negative, like so, what I would expect is that there's a voltage difference between here and here. Why? Well, we just reversed our thought process. If there is positive charge here and negative charge here, then there are electric field lines going from here to here. And if there's an electric field line, you might remember that if I integrate the electric field line with respect to distance with a minus sign, I find the voltage difference. I won't write that equation, that's okay, but we know that if there's an electric field, there must be a voltage difference. So there must be a voltage difference between here and here. So we put our voltmeter and measure the voltage difference. So that would be some voltage difference like so, high here, low here. And then we will say that the capacitance of this structure is given by the amount of charge that I placed on the capacitor, positive, negative, so Q, divided by the voltage that the capacitor now has generated from that charge, so Q over V. That's the definition of capacitance that we use. All right? So for any structure in any situation, we can bring some charge on the capacitor, so positive here, negative here, measure the voltage difference, use this equation to find the capacitance. All right, so of course this also tells us that Q is equal to C1V. So both of these are useful depending on what's the input and what's the output, right? So the input could be charge and we're looking for voltage. So in that case, V is equal to Q over C1, or the input could be voltage, we're looking for charge, however we want to do it, cause and effect. All right, now if we use this test, this measurement technique, we can find the capacitance of a structure like so. So let's write that here. So we say capacitance of a parallel plate structure. So one simple way of building a capacitor is to take two parallel plates. So let's take that. So here's one plate, here's another plate, and they have a vertical distance of some amount. So let's say the distance between the two plates is D, and then each of these has a certain area, let's call that A. And in general, the spacing between these two plates is filled with something. The spacing, it could be vacuum, it could be air, or it could be something else. And the reason we might fill it with something is that we want to get a larger amount of capacitance. So if we fill this area with something, some non-conducting material, so let's go here. Okay, that material has a particular parameter, and that is called the permittivity, and denoted by epsilon. Okay, so epsilon has certain value for vacuum or air, but as we go to other materials, epsilon becomes larger. So If I build a structure like this, and it has two wires connected to it to give me the two terminals like this, and then using this equation, one can prove, we proved it in physics, that the capacitance of the structure is given by epsilon, this value here, times the area of each plate divided by the distance between the two plates. All right, this is true only for two parallel plates. The plates need not be rectangular. They can be any shape as long as they have the same shape and they're exactly on top of each other. All right, so this equation tells us all sorts of interesting things. It says that the capacitance between two plates becomes larger as the plates themselves become larger. So that's a useful rule to remember if you're trying to build a larger capacitor or a smaller capacitor. If we're trying to minimize the capacitance somewhere because it's bothering us, we have one possibility is to minimize the area of these plates. And it also says that as the distance between these two wires decreases, the capacitance also increases. So as you bring the two plates closer and closer, the capacitance increases. So again, if the capacitance is bothering us, we have to increase the distance so that as these go farther and farther from each other, the capacitance, of course, will be minimized. All right, so those are the basic things we need to understand. All right, now, with this definition of capacitance, this equation that governs the behavior of a capacitor, we can also go ahead and calculate the relationship between the voltage and the current of capacitors. That's essential for circuit analysis, right? Because most often we are interested in currents and voltages. For resistors, Ohm's law applied, and it was easy. V is equal to I times R. For capacitors, that's not true, so we have to figure out what equation we can use. All right, so let's write that here. So we say current voltage relationship. So actually there are two of them, so we'll just say relationships, depending on whether we're going from current to voltage or from voltage to current. All right, well, remember the definition of current from the first lecture. We said that current is the rate at which charge is passing through a wire or through a device. So if I have a capacitor, C1, and I'm sitting here and I'm measuring some amount of current, and then I have a voltage like so. The current that I'm measuring here, if I go sit in this wire and measure the current that's passing through, that current is actually the derivative of charge with respect to time, right? That was our definition of current. So we also have an equation for Q of a capacitor, like this. So now we can go ahead and take the derivative of this to find I. So we say I is equal to the derivative of the capacitor. Let's say the capacitor itself doesn't change with time. That makes sense, right? Here, these two plates are fixed. They're not changing with time, so that's not a function of time, so C1. And then the derivative of the voltage with respect to time. So this equation tells us that the current through a capacitor is given by C dV over dt, or C1 dV over dt. That's an essential equation that comes in handy when we are analyzing circuits that contain capacitors. And as we build more and more interesting and complex circuits, of course, we have to master this equation and its manipulations. All right, so with this, now we can make some observations. So, some observations. So number one, unlike resistors, for which V equals 0 results in I equals 0. Remember, right, from Ohm's law, we know that if V is 0, I has to be 0 and vice versa. That's not negotiable. For capacitors, that's not true. Capacitors can have V equals 0, I not equal to 0, or V not equal to 0 and I equal to 0. That's interesting, right? Okay, so how is that possible? Well, let's think about this one first. So V equals 0, I not equal to 0. Is that possible? Sure. So all we need is for the derivative to be not 0, but for V itself to be 0. So here's the situation. So if you have a voltage as a function of time, this voltage here, that looks like this, and it's crossing 0 right at this point in time. So what you can see is that V is 0 at this point in time, but the derivative is not 0, so the current through the capacitor is not 0. If I create something like this across this capacitor, then I have a current at that point in time which is not 0. Okay, so that's one example. How about the other case? V is not 0, but I is 0. Is that possible for a capacitor? Sure. If I have a capacitor that has a voltage on it, and I just leave it by itself. So consider V is not 0, I is equal to 0. So I charge a capacitor, and I leave it alone, right? It's not connected to anything. So it has certain voltage, and it has no current through it because it's open circuited from the rest of the world. Okay, so these are interesting properties that we observe for capacitors. All right. The next point about capacitors is that the voltage can be found from the current. Right? So I guess I'll just put the here to make it grammatically more correct. So here I have expressed the current in terms of the voltage. What if I want to find the voltage in terms of the current? Well, I just have to divide by C1 and take the integral of both sides with respect to time. So I will write V, the voltage on a capacitor, is equal to 1 over C1 integral of I dt from some time to some time, so maybe from 0 to t. Okay, so let's assume that I have a current passing through the capacitor. Where does it come from? From somewhere, we don't know. Could come from some circuit, from a battery, whatever, right? That current has some behavior as a function of time, so some I of t. And then I let that current flow through the capacitor for some amount of time, from 0 to t. And then I ask, from that current, how much voltage have I accumulated on the capacitor? This is the voltage, 1 over C1 times that. And this makes sense, because when we push current through a capacitor, the current itself consists of charge. So replacing charge, coulomb by coulomb, on the capacitor. And we placing positive charge here, negative charge here. We're building up the charge on the capacitor. And because the charge and the voltage are linearly related, as we build up more charge, we build up more voltage. So that's why we have to have this integration here. All right, so that's the equation that relates the voltage to the current. If you don't remember this, not a problem. You can always start from here and then find V in terms of I. Okay, now with all of these, we can go ahead and look at a few examples. Let's start with an example here. Change the color to green. Okay. All right, so I will perform the following experiment. I have a voltage source here, and I have a capacitor. Very simple. This voltage source is given by, so I'll write it V of t is equal to alpha t for t greater than 0. Okay? And my objective is to find the current that flows through the capacitor as a function of time. All right? So it should be easy enough, right? Let's take a moment to see what this means. So I'm assuming that V of t is 0 before time 0, and then alpha t above time 0. You can also write this as alpha t u of t, is unit step, to make sure that it's 0 before time 0. So let's plot this first. So here's what V of t looks like. So before time 0 is 0, and then after time 0 it's alpha t. It goes up linearly with time. This is what we call a ramp. So that's a ramp. All right, so that is the voltage applied to the capacitor. So we'll call this V of t. Then how much is the current? The current will be equal to C1 times the derivative of the voltage with respect to time. The derivative of this is alpha as constant, and then multiplied by C1. So let's plot the derivative multiplied by C1. Remember always that there is a C1 here. It's not just a derivative, right? So I1, before time 0, the derivative is 0. The voltage is flat. So we don't have a current. And then beyond time 0, what happens? Beyond time 0, we have alpha for this derivative times C1. So it's just a constant value, and it goes like this. So that's alpha C1. That's the current through the capacitor as a function of time. Okay, so a few interesting points that arise here. Number one, if the voltage on a capacitor changes linearly with time in a ramp, as in the form of a ramp, then the current through the capacitor is constant. All right? Can I turn this the other way? Can I say if the current through a capacitor is constant with time, the voltage across the capacitor rises linearly with time? That's good too, right? It goes both ways. So yes, we can also say it that way. So if somehow I manage to create a current through a capacitor that is constant, so let's say 1 milliampere at all times, then I can be sure that the voltage on the capacitor grows linearly with time with some slope, right? So that's one good thing to know. Second point, as is obvious from here, if the voltage on a capacitor is not changing with time, the current through the capacitor is 0, right? That's what we have to remember. So let me write that here. Maybe I'll go to the next page because I have to go to another example anyway. So let's go to the next page. So important points. Number one, what we see is that if the voltage on a cap is constant, then the current, which is C1 dV over dt, is 0. All right? So if in some situation, in some circuit, we see that the voltage on the cap is constant, the current through it is 0. The voltage doesn't have to be 0. The voltage just has to be constant. So That's something that we have to remember. It looks trivial by looking at this equation, but when you enter circuits and there are lots of things flying around, you just have to remember all these principles so that you can apply them readily. Okay, so second point. I'm going to write this in red because this is very important. So I'll say very important because we will see this over and over again. Okay, so for the voltage on a cap to change instantaneously, the current must be infinite. All right? Is that clear? Yes, so when we say instantaneously, we mean that the voltage jumps in zero time, right? So if I have a voltage that looks like this, so this is V, and as a function of time, zero, it jumps from 0 to V0, right? So if we know that this can be written as V0 U of t. U of t is the unit step. Okay, so we have that. Now, if I apply this type of voltage across a capacitor, so this is applied across a capacitor, right? So imagine I have a voltage source, and the voltage source has this behavior, and then it's applied across a capacitor, C1. The capacitor says, well, my current will be C1 times the derivative of this voltage. Let's go find the derivative. So the derivative of this voltage, so let's say I is equal to C1 dV over dt, C1 V0. What's the derivative of a step? It's an impulse, so that would be delta of t. So the current as a function of time will be like this. Here the slope is 0, here the slope is 0, no problem there, right? And here we have an impulse, right? So that's this impulse here. That's the current that needs to flow through the capacitor. An impulse is a quantity that goes to infinity for a very, very, very short amount of time, comes back to 0, right? So this equation says that if the voltage wants to jump in 0 time, jump instantaneously, jump abruptly, then the current delivered to the capacitor has to be infinite. All right? So now let's turn it the other way. Let's say the following, which is also important. So if the current available to charge a capacitor is less than infinity, right? Which is a practical situation, right? In none of our circuits can we deliver infinite current to anything. So if the current that's available is less than infinity, the voltage cannot jump instantaneously. So we say the voltage, the cap voltage, cannot jump in 0 time. So I say 0 time, you can say instantaneously, however you want to do it is fine. The point is that if the current that's available to us is not infinite, then the voltage cannot just rise in 0 time. So in reality, the voltage will be like this. So V, as a function of time, cannot go like this, right? It has to take some time to reach its final value. All right? Okay. So these are important points that we will visit numerous times in this course as we analyze circuits consisting of capacitors and resistors and inductors, etc. And we always go back to this equation, right? That's the basic equation that we have. That equation tells us everything we need to know. If we are in doubt, we always go back to that equation. If you go for a job interview and someone says, can the voltage on a capacitor jump instantaneously? And you say no, the person will say, why? Why not? And I have to explain. You can't just say, whoa, I learned something in basic circuits I don't remember. You go back to that equation, you say, if the voltage wants to jump instantaneously, the current has to be infinity. In practical circuits, we don't have infinite current, so we cannot. All right, let's look at another example. All right, this example, I have a current source, I1, driving a capacitor, C1. And I have a certain waveform for this I1, meaning I1 as a function of time. It looks like this. So I1 is 0 before time 0. Then it jumps to I0. It stays at I0 for some time. And then comes back to 0 at time t1. Okay, so that current is what's going through this way to the capacitor. And now I would like to plot this voltage as a function of time. All right, very simple. Okay, so in this case, we have the current flowing through the capacitor. We're looking for the voltage across the capacitor. So we go back to our fundamental equation and say, well, I have the current, I need the voltage. I have to divide by C1 and integrate with respect to time. All right, so no problem. Let's go ahead and do that. I'll try to squeeze it here. So I say V is equal to 1 over C1 integral of 0 to T of I1. I1 looks like this, right? So it is I0 from 0 to T1. So this has to be T1, this has to be I0, and then this has to be dt. This is true only for T between 0 and T1. Is that okay? All right, so then if I write that, sorry, actually this has to be T because I'm looking for a general situation, but this is true for 0 from here to here. So then that will be 1 over C1. Integral of I0 is constant, it comes out of the equation, and then we just have T evaluated from 0 to T. So that would be T. So that's the voltage as a function of time, I0. Okay, so let's plot that. I deliberately left space here so I can plot the voltage. So the voltage as a function of time looks like this. Before time 0, we have a 0 volt on the voltage on the capacitor. How do we know that? Well, actually we don't. It's possible that the capacitor might have had some charge before we started this experiment. But our assumption here always is that if we do not specify the initial charge on the capacitor, then the initial charge on the capacitor is 0. So I started out with a completely discharged capacitor. I connected the current source to it, and I let go of the circuit. And the circuit started with, okay, no charge, we have 0 volts. And then the current came in, started charging the capacitor linearly with time. So we charge it linearly with time up to this time here, T1. And then what happens after T1? After T1, this current is gone to 0. When a current source goes to 0, we throw it away. It's an open circuit. From now on, this capacitor is sitting by itself, not connected to anything, holding the last voltage that it had, this voltage. So this voltage and the charge will reside on the capacitor indefinitely. So what we see is that the voltage across the cap starts from 0, rises linearly with time, and then stays constant in this experiment. Okay, so does this linear behavior reminds us of something? Yes, previously we said that if we charge a capacitor with a constant current, the voltage on the capacitor grows linearly with time. And that's what we are doing, right? We have a constant current from here to here, and during that time, the voltage rises linearly. All right, now let's make the situation a little more interesting and ask. So let me change the color of my pen here. What happens if this time is reduced by a factor of 2? Okay, so for example, the current only lasts up to here. Then what do we get? We have the same integral as before, 0 to t. From 0 to t1, t1 is now here. And we have the same equation. The equation hasn't changed. But the last time available for the voltage is over here, not here, because the current only lasts until this time. So this will go up to halfway, and then it'll stay right there. So if the current jumps to 0 at half the time, then the voltage goes up by half and then stays constant. Right? So that's sort of interesting. Why does that happen? Well, because remember that this integral of I is calculating the area under the current waveform. The area under the current waveform was this much before, but now for the red case is only this much. So it makes sense that this voltage drops by a factor of 2 after this integration is finished. So this is not quite accurate, but this should be like that, right? Okay, all right. The next question I want to ask is, I see that this voltage in either case takes some time to reach that high level. Takes some time, right? This amount of time, this amount of time. What can I do to this current source so as to shorten this time? Right? I want to go like this. How do I do that? Right? So let's make sure our timing is good. Okay, our timing is good. Okay, so I will raise this question. How do I make the charging process faster? Right? So I would like the voltage to change like this. So previously it was changing like that, right? But I want it to go like this. So what's your guess? How can we do that? Well, if you look at these results, what we see is that we are hoping to reach this value in a shorter amount of time, so t is less. But we also need to deliver a certain amount of charge to the capacitor to reach this voltage. So I want to deliver the same amount of charge in a shorter amount of time. What does it mean? Same amount of charge, shorter amount of time. That's a higher current, right? Because current is the derivative of charge with respect to time. So for that to happen, we need to increase I0. So I0 previously was like this. I0, the current was like this, right? What I have to do is I shorten the time, but I increase the current. I shorten the time more, and I increase the current more. So as I shorten the time, but I increase the height of the current, eventually it approaches an impulse. So for this voltage to change abruptly like this, the current needed here, this current, has to approach an impulse. Narrower and narrower, taller and taller. And of course, that's something that we saw before. This just reconfirms our intuition about the necessary current for an abrupt voltage change across a capacitor. This concludes the lecture today. I will see you next time.